So these are the frequency band designations, and the lot of applications were involved, and the thing is, the main concentration is marked in red, highlighted in red color. So these are the frequency applications where we can work, and also I have worked. And these band designations are taken from the FCC standards, and these particularly in this particular band of resonance, in these applications, whatever the antenna design that I have going to discuss will be applicable, and those designs will be displayed. Yeah, next. So coming to microstrip antennas, uh, microstrip antenna configurations are different shapes we can use, and microstrip antenna is combination of three layers, and one is ground plane, and another one is patch. These two layers are or sandwiched in between. I mean, in between these two layers, there is a substrate, that is the electric substrate, and the figure which was displayed here is proffered microstrip patch antenna. We can use many shapes in order to design antenna, and that is triangular shape, square, circle, semicircle, annular ring, and ellipse, and pentagon, and hexagon. Here, most probably, most of my designs are belongs to square and circle. So the novelty issues, and in order to generate circular polarization will be discussed. Next. So the point is, the operation, the basic operation of microstrip antenna is like this. Whenever two metallic layers are there, the cavity, the rectangular cavity will be formed in between patch and ground plane. In the substrate, there are standing waves will be generated whenever the feed is matched with the patch load. So that means that those standing waves try to escape from the patch antenna. So if they're trying to escape that patch antenna, you have to match the impedance. So the impedance is generally 50 ohms. We'll consider here, and whenever, according to maximum power transfer theorem, if source impedance is matched to the load impedance, then the maximum power will be delivered to the load, so that the fringing fields in between in the patch and direct ground plane will try to escape from the radiating edges of the patch. So these radiating edges uh, will generate fringing fields. Due to this fringing fields, the radiating edges will be looks like a bit longer. That longer distance will be considered as delta LP, and these through these edges, according to maximum power transfer theorem, the load will be delivered to the edges, and that whenever there is a constructional change in the patch there, because the ground plane is somewhat bigger when compared to the rectangular patch, so there is a constructional change, so that radiated power is going to try to escape. Like a dipole, what we have seen, whenever you bend the dipole at the edge, so you are going to form accelerated and decelerated electrons. So they are trying to escape from that particular nature. They are trying to detach from that particular radiating element. So the same way, the fringing fields are trying to detach from this particular radiating edges, so that is how the radiation is going to happen. This this phenomena will be applicable for any shape of the antenna where the radiating edges are formed. Next. Right. So let us see the conditions of CP radiation. So first, in order to design an antenna, first you need to have a frequency and epsilon r. You need to decide which frequency you wanted to, at what frequency for what applications you wanted to design an antenna, and on what substrate. So what substrate means the epsilon r value of that particular substrate. If you decide these two parameters, then you can find out length and width of this antenna according to this formula that was given by Studgman and Thiele, antenna radiating systems by Studgman and Thiele. This is very simple formula. So with this formula, you can find out length and width of the patch according to the radiation frequency and epsilon r value. And if you wanted to generate a circular polarization, So two orthogonal modes should be generated in x direction and y direction. So both should be perpendicular. So whenever if you want to generate two orthogonal modes, next slide. If you want to generate orthogonal modes, excuse me. Yeah, if you want to generate,
May I request the participants to mute yourself, please? Dr. PSR, sir, you please mute yourself. Okay, thank you.
So whenever these two orthogonal modes are generated, so if it is tending towards right side, that means right side of your hand, then it is going to be clockwise. A clockwise direction is going to be called as right hand CP. And if it is tending towards right hand, it is circling towards right hand, the EX and EY magnitudes of EX and EY electric fields, the orientation of those electric fields towards your left hand, that is anti-clockwise, then it is called as left hand circular polarization. So like this, only thing is you have to bring the constructional change in order to generate two orthogonal modes. If you bring a constructional change, that is called asymmetric nature in the generation of EX and EY, then you could able to generate circular polarization. That is the only phenomena on the shape side. There are other phenomena also there. You can use two dual feeding technique, and you can use microwave network to feed the elements, different elements. There are other techniques are also there. But according to the shape, if you want to bring a circular polarization, if you want to get a circular polarization, these asymmetric nature of this particular shape, you have to bring it through slots or other configurations that I'm going to show you, right? Next. So this is what I'm talking about, the EX, EH and EV, horizontal direction and vertical direction. These two electric fields, if you bring any asymmetry in the structure, these two fields will, the electric field locus, you can call it as a locus of this tip of the electric fields, EH and EV, are going to rotate. In left-hand side, it is going to be left-hand circular polarization. In right-hand side, it is going to be right-hand circular polarization. Next.